I'm Andrew Rove, Australian Bureau of Statistics. I wonder if I press the button, it'll go, oh yeah. So the ABS is a federal government agency for collecting statistics to improve decision making. So we're responsible for census, CPI, unemployment, balance of payments, and plenty of other ones. We've got plenty of statistics and we like to give them to anyone who comes along and sell them to people who want a lot more detail, so we can buy that. In this presentation, I'll show you techniques that are used to reduce the time from a standard deduplication run from 19 hours to almost 1 hour. So what's a deduplication? I think the next page. Australian Bureau of Statistics must check the census to ensure that people are only counted once, and this process is called deduplication. We have large data numbers and we have very high accuracy standards for accuracy, but not too high standards for talking sensibly in presentations. So we use a system from the ANU called Febrile to process the data. So let's have a look. So Febrile is a freely extensible biomedical record linkage. It's written in Python and designed to handle hundreds of millions of comparisons using dozens of parameters. It was developed at the ANU by Peter Christian and Tim Churches at the Supercomputing Centre. So we took that over. And initially when we were running it, it took an awful long time. So we had a standard job of about 200,000 records and it would take 19 hours to run. And this was on, our Xeon Windows Server 2010 with 196 gigabytes of memory. So it should have gone fast, but it was pretty slow. So we had 20,000, and then we had another job, which was to do all the census to check the duplication, and it would take 7 days, and then it just crashed. So that wasn't too good. And the thing with census is that we have to get everything done within a certain time frame by legislation. If we don't finish, then all the data that can be used to identify people is removed. So we've got 1 more month, 2 more months I think until December, then all the forms and all the data which could identify someone from the census is pulped and destroyed and all the drives are wiped and all the databases are cleaned out, so all we have left is the summation, the general stuff. You can't identify anyone after that date. So we have a time period. So taking 7 days to run and then not doing anything is not too good. So I was asked to enable Febrile to make it go faster, and these are some of the lessons I learnt in improving the performance of Febrile. So lesson number 1. I don't know if I've got lost anything. Febrile is written to use multiple cores with MPI, which is a multiprocessing library, but no one at the ABS had ever gotten to work, so that was the number 1 thing to try and get that work. We had Windows virtual servers with 8 Xeon cores and 190 gigabytes of memory. So there's a potential there, you have 1 core, it takes 8 hours. 8 cores, obviously, it takes 1 hour. So that's ideal. So that was the potential there to make it much faster. Okay, calm down. Okay, so after a bit of fiddling around with the multiple cores, this is the results I got. So we started off here with 1 core, then once we've implemented MPI, 2 cores, you can see down it's practically half the speed. 3 cores, not too better. 4 cores, it's not quite down here where it should be. And as you get more and more cores, the improvement sort of lessens off a lot. And then you can see this big bar graph up here. As soon as you go across 2 machines, which you can do with MPI, you can set up machines so they all behave like one. You go up there. So there's obviously something happening here. What was happening there was it was just taking a long time to communicate and synchronise all the data between machines. So I gave up that idea. I had visions of a huge grid encompassing everything in the Bureau, and I'd take over all the resources and everything would be done immediately. Megalomania is often sort of frustrated. Okay, so the next one. Okay, I'll go with demonstration of single core and then multiple core. Now let's go to the demo and see if that crashes. All right. So I'm going to add up 1, 2, 3, 4, 5, 6, 100 million with 1 core. Okay, so that took 2 seconds. That's pretty good. Maybe we'll just make it a bit longer so it's a bit obvious what's going on here. So it's taking longer, obviously. Come on. Maybe it's taking too long. You'd think it'd take 10 times long. Okay, so it does. So it's 16 seconds. So now we put an extra parameter at the end here, which is how many cores are going to run. Apparently my PC says it's got 4 cores, but actually it's only 2 cores with hyper-threading, so I'll just run it with 2 cores. And that should go twice as fast. Come on, come on, go, go. There you go, see? If you can run your program on more than one process, you could potentially halve the number of times it takes. So what this does is, if you want to have a look at the code, okay, where'd it go? Okay, so what we're doing here is we're just counting the number of CPUs, working out how we're doing, we're creating a queue for each CPU, then we're going down using the multiprocessing module, which is a standard part of Python. Every version of Python, I believe, has got it, so you don't need to install anything else, which is great. And you just say, I want to run this function on all these other processes, and I start it, and then you just wait for it to finish. In that bit, the join bit means wait for it to finish. I don't know why it says join, not wait for everything to finish. There you go. And once you do that, you can just up in your function to do the adding up. You just have to a method of ways that each process knows which bit of it it's adding up, then it puts the result into the queue and returns it. So that's the hard part of multiprocessing, is deciding how to divide up your job so things can operate independently. And then understanding how to coordinate and bring them all back together again. So we'll go back to the demo, to the presentation. So here I've got a screen dump of it working on one of our servers with 8 cores. And beforehand, it took 12 seconds, and afterwards 1 second. So that's a pretty good speed up. So if you could apply that to all the job, you can go from 19 hours, 19 divided by 8 is about 2. So then you can get 2 hours, so that's pretty good. So that's the sort of thing we're hoping for. So we do that. Okay, so we put in the MPI, and that's what happened. We went from 19 hours down to 1.5 hours. That meant that statisticians can use, they said, oh great, your job now, instead of taking 90 hours, takes 1 hour, let's put more data into it and change all the options so we can get more detail and put it back up to 19 hours. And that's what users are like, I believe. Okay, so there we did that, and that meant that not only they could do their jobs within 1 day, but they could actually do multiple jobs, so they could make mistakes and enhance it and change the parameters. It was really great for them, they loved me. And I got an award. I think I got $50, so there you go, that's what happens in the public service. It's almost the same award as for going to a meeting once for something else that's been organised and never attending again and getting an award for that. So I was pretty pleased. Okay, so once we did this, we would then reduce the time and we allowed the whole census to be duplicated. So that's 20 million records compared against 20 million other records, and you got perhaps 400 billion comparisons or 400 trillion comparisons, and that was all. We could do that within about 3 or 4 days, so that was pretty good, and it completed. Okay, so next some more. Okay, I did this one. Okay, so it's another things that we did when we noticed that we were running Python 2.4 because no one needed to bother to upgrade. And then I looked at it and I said, okay, if you upgrade from Python 2.7 without changing any of your code, it'll go 30 to 40% faster. So we did that immediately. Another thing was that through the code, there was all these if false to do debugging. Take all them out, goes another 20% faster. So there's a lot of things that people don't notice, things like that. Another thing is when we were reading files, we just read them and using the standard Python calls, but if you change them around so you can memory map the files into the virtual memory, you get another 20%. So just by a couple of simple changes without having to change any of the logic of your program or any new packages, what's that? 30 plus 20 plus 20 is something a lot. I don't think sort of you can add up percentages, that's a sort of statistically invalid thing to do, but never mind. All right.
What happened to the debugging?
Well, it's sort of like debugging. When the bloke wrote the code, he said, if I compare these results to those results, do they come out expected, print it out? So we just went in there where it had all the print statements. No, it just took them out. Because you had all these print statements, if debugging mode, if debugging mode, if debugging mode, if debugging mode, print statements. So just get rid of them all, and that saves a lot of time. Especially you have a loop. Like if you're looping 400 trillion times, if something takes 0.0001 seconds, multiply that by 400 trillion, that's a lot. So when you're doing little numbers, it doesn't make much difference. But when you're doing big numbers, you go down and take things like that, it really makes a big difference. Okay, and here's the specific techniques that can be used with any Python standard installation. Don't need any other packages, don't need NumPy or anything else like that. And like I was saying before, large numbers comparisons cause small delays and efficiencies that can build up into large blockages. So when you're talking really big numbers, little tiny numbers are significant. Does that make any sense? There you go. Okay, so the first one is you use X range instead of range. Now this might be something that's been said all over the place, but it's easy when you're writing out a for loop just to say range and treat it like it's a C for loop or a while loop, but it doesn't quite work like that. So range has to generate a list of the numbers before enumeration starts. So it's not like a for loop in C where you just increment it and just check it. So you've only got one little value there, you only got it in, 4 bytes, 16 bytes. When you're doing a range, it'll create the whole range in memory and then put it in the for loop and iterate across it. Which doesn't seem to you don't notice that if you're doing like 1,000, 10,000, 100,000. What happens if you're doing 100 million? You've got 100 million int objects in your range. And that could take up a lot of memory. Even with 196 gigabytes, it's significant. It can take time to produce. If your number is really gigantic, it can take up all the memory and the thing crashes. Okay, so I've got an example here. Where we are. So this is my code here. Can you see that well enough? No. Yes? Yeah. Oh, good. Okay, at least one person can, so that's all right. Okay, so what we're doing simply here is we're making a range up there. What am I doing? Oh, yeah. Okay, so here I'm just working out how long it actually takes to create a range before you do any processing. There I'm creating a range, and now I'm using X range. And X range is different. I think it's an iterator. I can't remember the details of it. It's almost like a while loop. While 1 is less than 100, 1 plus plus, X plus plus. Okay, so let's run that. What's that? How many zeros are there? I think that's 1 billion, isn't it? 100 million. Okay, so it took 2.5, almost 3 seconds to create the range before it actually did anything. So actually you're not achieving anything by using a range. You're slowing down before you can do any processing. So now so there you go, 16 seconds to, I don't remember what it did, but it did something. Added them up. Okay, there you go. And now X range, if your fingers crossed, should go faster. Ah, cheap. Oh, well, that's pretty good anyway. So that's one second. But yeah, I can see, we go into the performance monitor here. You can see here, that's where it created the range. So you've used up almost all your memory creating a range just to do a little loop. So you've got to watch out for things like that. Okay, next one. Pickle parameters. Now in our application it has to store state, so it keeps things in pickles. It also uses pickle to do its MPI synchronization. So we have large data structures in lists and arrays and dictionaries, and what the pickle thing does, it pickles them up, sends them to the other hosts where they're unpickled. So that's how we sort of send things around using MPI. You pickle them up, and then you say, copy this memory to the other processor, and then it will unpickle it. So you're probably familiar. So pickle makes a byte stream representation of pretty much any Python object which is serializable, and it puts it into a structure, and then you can unpickle it and bring it back out. Now the default parameter is for ASCII. Storage, which is not ideal for speed. It's also big. But it's a default parameter, so people who are not thinking about it, they'll just go pickle, it'll work, and they go, hooray, next part of the project. They won't think about it anymore, which is what I did when I started. But pickle has a protocol parameter. There's also a CPython library, which is often mentioned, but if you've got a bit of a code working, you just keep going. You won't think about it because it works. I mean, what do you care? Okay, so now we've got an example. There we go. Oops, not that one. This will probably work, but anyway. So let's just run that. Okay, so what do you got? You've got 2 million items for making a pickle. I timed all these beforehand. I should only take about 30 seconds to run each example. But presentations, everything slows down, the internet goes away. And when you're up here, time accelerates. Have you ever noticed that if you're doing a presentation? Come on! I bought this computer to play World of Tanks, so it should be fast.
What do you set your protocol to?
Okay. Well, while that's running, okay, so what he asked, what do we set the protocol to? So we'll have a look at the source code. Oh my God, 2 minutes, I have to speed up. Okay, 10, whatever. Okay, so if you go down here and you look at your pickle, I've got C pickle, just pickle, and this one you got protocol equals pickle highest protocol. So if you do that, it'll automatically pick up the fastest, most efficient one. So that's what you do. But you've got to remember, when you're unpickling, I don't know if it works it out or not, I can't remember. So then we go back to the example. Why have I got 2 DOS botches just to confuse me? So there we go, see? Ordinary pickle, 50 seconds. C pickle, 7 seconds. Pickle latest protocol, 1 second. You've reduced the time you've taken to store your data to 1/50th of the time, just by changing your protocol, a parameter, and including a different standard library which works exactly the same as the other standard library. Oops, wish I wouldn't. Yeah, gotcha. No, that's the wrong one. It's this one. Here we go. Next one, shelf parameters. Now, shelf is a dictionary which lives on disk. It uses pickle as its protocol for storing things on disk. So if we put a protocol parameter onto a shelf, we can speed things up. So I'll just give a demo of that. Not that one. There we go. So it should also take about 20 seconds. Now we use shelves to store results of each run so we can compare them. Now before it wasn't doing any particular protocol, so we had shelves of 10 gigabytes, which would take a long time to run. So there we go, 21 seconds to normal, and if things work out, I think it's about 5 seconds. So there you go. Just by changing your protocol, you can make that part of your application, complete in a quarter of the time. And if you're writing out a 100 gigabyte or a 10 gigabyte file, which takes 20 minutes or an hour, a quarter of a time, it really adds up. Okay, so next one you can do is file handling techniques. Now in our process, we have data files millions of lines long, and it was just using Python read line, write line, read line, write line. So what we do, just by changing a few parameters, you can speed things up. So let's have a look at the code for a second. All right, okay. So just naively, where we are, we could just do a bit of code like this. We just read a line, write a line, then write it out. Now obviously there are better ways to write it, but you might be doing some processing in the middle. So then we got that one. Now you can also do, perhaps you can read a line, write it to a bit of memory, and then write it all out in a big blob. Or you could read it all in a big blob, and write it out in a big blob. Or finally, you can read it all in a big blob as a memory map file. So this is an example of memory map filing here. So just do that, and that will make the file appear like it's a big string. And you can do Python slicing and all sorts of string operations on it. And it sort of maps it into virtual memory. So it's dramatic how much difference it makes. So we go look at a demo. Whoopsie. So here I've got about 4 10 megabyte files I'm adding together. Maybe I should have made these demos a little bit quicker. Yeah, it's not too exciting watching nothing happen, but because to get speed up, you have to remove the debugging. Otherwise, you could say, reading line 1, reading line 2, reading line 3, reading line 4, reading line 5. If you ever attempted to do that, don't do that, because that's wrong. Even though it's comforting. Okay, so we go. So we do the first sort of naively one, line by line, and we get 26 seconds and 7 megabytes a second. Now, we should be getting faster, so the little cursor should go away soon. Here we go. Read it in, read it in lines, write it out by blocks. That's a bit faster. That's pretty good. Because when we finish doing it, okay, you're reading in block, write it out by block. That's a lot better. You're reading the block and write it out with the memory map module. There you go. That's 1/6 of the time, isn't it? No, I don't know. 26 divided by 4. That's pretty good. Okay. Okay, next one. Okay, I showed you that one. Okay, here, local versus global. Now, this is a silly Python trick that you often see, but you don't realise the effect of it. So what you can do, the way that Python looks up things, it looks at first if it's in a local list of functions, and it looks in a global list. And every time you call it, it does that. So what you can do is if you've got a function which is one of the built-in functions like max, you can make it into a local max and minimum into local minimum. And that way, instead of looking it up in the global list, it looks up in the local list, and it's faster. So let's have a look at the demo of that. Yeah, I can't. So we're going to do this 1 million times. So there you go, that's the global one. That's the local one. Now, you see there's a difference there, little tiny difference. But if you're doing that 400 trillion times, that really adds up. So that's the silly Python trick. 5 minutes, okay. Okay, so that's a good one. And now list versus dictionary. This is an interesting one where if you don't choose the right collection size, things work perfectly when you've got little amounts of data, but as you get big amounts of data, it can quickly go bad. So when you're trying to, if you want to, you've got a list of numbers, and you want to say, is this number, I've already seen it, is this number, I've already seen it, have a process number, you might put it in a list, because that makes sense. You put numbers in a list. So what happens if you do that? Okay. Okay, so here we go. First of all, you've got 100 items in your list, and the first number is the list, and the second number is a dictionary. You've got 200 items, 300, 400, 1,000, it's 0.2. Come down 10,000, it's 1.9. 100,000, 200,000, so you sort of it's going up in accordance with the size of the list or the dictionary. But every time we search a dictionary, the time is 0. So if you can just look in your code to see whether you use a list, just take it out and use a dictionary, because they pretty much operate in much the same way. A dictionary takes up a little bit more memory, but it doesn't make much difference. So I wrote a little bit of code naively, and I tested it out with 1,000 records. Oh yeah, it works perfectly fine. Didn't notice it, but then we put it into production, and we're doing 400,000, 1 million. And the user said, oh, the server crashed. It got to this point and it crashed. It just stopped, nothing working. And of course, it wasn't crashed. It was just sitting there going through a 10 million line list looking for one number. And then we just looked at that and I go, bang in the head, and changed it around. We went from 10 minutes sitting there doing nothing to 0. Okay, what's the next one? Okay, this is a little bit more complicated. So C libraries. Now there's another presentation yesterday where you can use the C types package to look up any C library that's already existing. What you also can do is you can write your own C library to do things. Okay, so let's have a look at a bit of simple code here. Where are we? I can't find things. Okay, so this is our example code. So we've got a silly operation. What it does is it adds up all the ASCII values of a string. So I wrote another one called multiply deal, which has that similar function but in C. So we have a look at that. I've got it here. Got to see something with a C extension. Oh, there it is. Okay, so then we just do like this. This is all you need to write in Visual Studio. It's trivial, but we're just doing exactly the same thing in C. So what's going to happen? Let's stop that. Okay, so we're going to add up. I think it's a very big string, add up all the ASCII values. I'm going to do that 20,000 times. Hey, that's another one of my programs. Okay. Now you can see here, you did 20,000, it took 12 seconds. But the DLL, look, 0.01 second. So it's 100 times faster. And writing a D like that could have taken you maybe half an hour, and the biggest amount of time will be waiting for Visual Studio to load. And the second biggest time was to try and find out where it put the DLL. So with a simple little bit of logic, changing from one language to another, making a DLL 100 times faster. So we had one particular function in this thing which would take two names and compare them and give you a number about how close those two names were together. And I changed that to a DLL, and that took 30% off time of the things, and that was being called every time we did a record. It was being called millions and millions of times. So if you can look at your profiling, look at see where things are going, go in there, and you can really, with a little bit of work, you can make things 100 times better. Now, that's pretty good. We all know C, don't we? Because Python's written in C, and we all build Python from the source, don't we? Well, I don't either. Okay, so there we go. And I think that's the main things that I've done. You can just do some simple things, changing protocols, changing parameters, and changing language use, and you can get things going a lot faster with little effort. Okay.
Cool. So we have a few minutes for questions. If anyone's...
Thanks, that was a great talk. I just wanted to quickly add with the list versus dictionary thing that you could also use a set, and that's the same performance as a dictionary, slightly different semantics.
So I have a question about the file going through that large. Well, you only got small files there. So I have a situation where I've got like a 2 GB file.
Yeah.
And so like you've got examples there where you're doing it like not a very Pythonic way, and like kind of there's another way to do it, which is you just go basically you just go open the file and just go full line in file, and you just go through it that way. And I don't know what performance difference it is with an mmap file or not, but I'm just interested to see if you've tried that just out of interest.
Let's have a look. Okay, so here's the code. There's a number of ways you can read files in Python. If we go up the top here, the very simplest way is to do it like this. With open and write. But I didn't show you that because that was quicker than the other way I did it. So that would have ruined my whole theory. But the reason you often can't do this is if you have got a 10 gigabyte file and you've got 2 gigabytes of memory, you can't because it tries to read all in memory as far as I'm aware. So you can't do that. So we were operating, giant files, and each processing core has to read the files. So that's the other thing you've got to be careful with MPI. Every process shares it's exactly the same memory. So if you wrote in a process that takes 1 gigabyte and you run on 1 core, and you say, oh, let's make it faster, we'll make it on 10 cores, what happens is now you've got 10 gigabytes because you've got 1 gigabyte per core. So it might work fine in your 2 gigabyte server, put an MPI, and then it goes, oh, why is it going slower? It should go 10 times faster, but it's because it's just all the memories are taken up. And Python just tends to crash when it runs out of memory. It's not special Python. Okay, now I've got another example, which might show you a little bit more complex. Where is it? I've got a couple of them. Where is it? I can't remember what it's called now. Oops. Okay, so we've got one up here. So this is a multi-processing version of counting lines in a file. Now, you can't just go read, write when you're counting lines in a file. It's obvious, it's a bit strange. Some people like to know how many lines are in a file. Because so they might say, I want to know how many lines in the file to know how long it takes, so I'll spend an hour counting all the lines in the file so then I can know how long it's going to take when I'm processing, but that's all right. So we had a bit of code in here which checks the lines of the because they correspond to records. So you want to know what's the maximum record number, that's the line file. So here you go, a multi-processing one. Yes, I know. I wrote a program because I get RSI, so it tells me to have a rest every now and then. Okay, so here we go. What we want to do is we count the number of CPUs here, and then we create queues for each process. And we put them all, make a queue, put it in the queue dictionary. Was that a list? That's a list. And then we call the function using the multiprocessing process function. So what it does, we come into this function up here, and then it opens up the file, memory map file, works out what the file size is, then it decides which part of the file it will count the lines in. And then you just wobble through there and read each line, tell you the other previous process where you are, and you add up, then you add them up in the end. And we're having a rest. And I think that's the end of my time, isn't it?
Okay, so we have a PyCon mug and a blend of African Swallow for you.
Ooh,
so please
coffee.
join me in thanking Andrew for his talk.